So I'm Roman. I've been
We
working in the
can't see
product
you.
for like 7 years. I've done a lot of stuff and missed a lot of stuff too, including this meetup. Sorry about that. And today's presentation is going to be on case non-constant. And so what do I mean by that? Oh, by the way, feel free to interrupt me anytime. Feel free to ask questions. The presentation, I think, is not going to be particularly long. So if you prolong the presentation by asking me questions, that is a positive. I will not look like an absolute failure. Yeah, let's go ahead. So, case non-constant. This is how currently we
Is that right?
branch. Sorry? No? Okay. This is how currently we branch on a Boolean. That's quite mouthful. You have this if then else built in, and you need to force it, and then you need to evaluate both of these branches, which is why we have delay, because if you just evaluate the true branch, then maybe you didn't want the true branch, maybe you wanted the false branch, maybe the bool was false. So that will be wrong, and that's why we have a delay. We evaluate this branch as well, the delay too, then we force the whole thing. It's a very long dance, and it's extremely inefficient. It's 11 AST nodes, if I'm counting them correctly. That is really, really inefficient. And as Alex Nemish put it, validators are just glorified if then else chains. So if your very basic if then else is this inefficient, your validators are going to be inefficient. But here's a new way of doing it. That's much more compact, and it's only one AST node. And that case thing, it comes from sums of products that Philip Wadler talked about before today. So we already have that. The only thing that we change is that now we allow case to operate not on just constant values from sums of products, but also on constants, such as Booleans. It has extremely simple operational semantics. If you case on a false, then you're going to pick the false branch as you would expect. Very simple. We allow the false branch to be alone without the true branch here. This is just, if you want to check that something is false, then you don't care about the true branch. You're going to fail anyway. And so we allow the true branch to be entirely omitted. So if this was case true and only one false branch, then that would be error. Similarly, we allow case non-true, and we are going to return the true branch, so this one. Very simple stuff. And this is just right off the bat how much performance that saves us for some very unspecific benchmarks. They do like, well, I mean, you can see it's prime tests and quints and like all these very general unspecific things from the no-fib set of benchmarks that GHC also uses, and that's where we got it from. And something also rather unspecific is sorting, and again you can see that it's pretty good. We have like minus 24%, minus 23 and 8%, minus 17 and 9, etc. So it's really efficient to case directly on a Boolean instead of, the whole if then else delay force dance with 11 AST nodes. And the best part is we already had the case node. We don't need to even cost anything. We just automatically get not only performance improvements, but also costing improvements. Again, right off the bat, you just literally compile if then else as a built-in to the new case thing, and right away you get better costs. And that's not even without changing any of the compiler. So we would still produce sums of products, booleans in the compiler. All the previous performance improvements were like that, but if we remove sums of products, booleans from the compiler entirely, then we can also get some pretty great improvements in terms of sizes, because we now no longer need to convert SOP booleans to built-in booleans. We just use built-in booleans everywhere, and those conversions apparently took a lot of size to just be there in the program. As you can see, not so much evaluation improvements. I guess that's because we optimize stuff really well. But yeah, it's kind of surprising that you can get so much size improvements just by removing conversions between SOP booleans and built-in booleans. But yeah, again, this all is very, very simple, and it gives us such great performance improvements that they are on the scale of us adding sums of products to the language. Similarly, branching on an integer is even worse. For booleans, we had to only do the whole dance one time. You have like if an else, delay, force, blah, blah, blah. It's constant size. It's big size, but it's constant size. For integers, it's not constant. You have a linear amount of overhead per equality check. That's a lot of overhead. I'm not even counting the AST nodes here. This is very inefficient to be doing all of that, especially given that we have sums of products, booleans, and built-in booleans. So you also need to do these conversions all the time. Sometimes not. Here, for example, you would just use equals integer, so there would be no conversions, but could be elsewhere. Anyway, so that's always very inefficient, and that's the new way. Again, just a single AST node. It is a multi-node in the sense that this is a vector. It doesn't have constant size. It does grow. So it is linear, but that's still the single AST node. And looking up something in a vector is a really fast operation, constant time. And you only need to deserialize the vector once. You do not need to traverse it. You don't need to traverse it at runtime a lot. Oh, I forgot to say an important thing. This is a joint work with Songon. So he implemented half the stuff here, probably even more. Props to him. Anyway. Yeah. The operational semantics for casing on integers is also very natural. Like if it's 0, then you choose the 0 branch. If it's 1, then you choose the 1 branch. Very simple. Also note that when we used if and else, the original branching on booleans, we had to evaluate all of the alternatives first, because if and else is just a function, and function always evaluate all of the arguments and put us in UPLC because UPLC is strict. But here you just choose the right branch without ever touching all the other branches. So this is a term. It's not a value. Oh, it's not a value. It's a term, and you just choose a term and you evaluate the term later without touching any of the other terms. Any questions so far? Yes. Can't hear anything, sorry. I cannot hear anything. Yes.
Can you hear me? One
Yes.
second. Okay, 1 second. Oh, okay, now we're doubling. Let's see.
Okay, can you hear me?
Yes, there's horrible echo, but I think I can hear you.
Echo is gone.
I can try one time.
And I can no longer hear you again. Sorry. Technology is hard. Should I just keep presenting? I don't know. Give me a sign. I don't understand the sign.
Okay.
Oh, I can hear.
Okay, can you hear now?
I don't know how this works. I'll take it like this.
It works. It works amazing. It's a
So,
miracle.
first question. I assume this works only on positive integers?
Yes, yes.
Okay.
You have to do the 0, 1, 2, 3. Yeah.
Well, non-negative integers.
Okay, yes.
Then lists, I assume it works like case choose list, the built-in, right? If it works on lists.
We will come to lists.
Okay. And then what do we do with built-ins that are now deprecated? For sure there is if then else. Then now
Yeah, so there is no longer a reason to use if then else as far as I can tell. They just stay there. What are we going to do about them? We have to keep them on the blockchain. We have to keep them in UPLC because they are on the blockchain. They are going to be evaluated for all the versions of Plutus. People have contracts with if then else in them. We have to keep evaluating them, and so they're just going to stay. I can no longer hear you again.
can you hear me now?
Yes.
Okay, sorry, I was keeping it far. So maybe I was thinking something using the UPLC version that is outside of the UPLC body. So to differentiate Plutus v3 from Plutus v2, we have UPLC version 1.1. We can try, I don't know, 1.2. And in that case, we can know which UPLC built-ins are allowed.
I mean,
but yeah.
sure, but why do I want to disallow them? Maybe someone.
No, just to understand if I understand that we need to keep them, of course, for backwards compatibility. It was just a curiosity. What if they are still around, given that they are effectively no longer needed?
So what one possible answer is the specialist case might be more efficient. So if you have a two-branch Boolean test, it's probably going to be more compact than the case statement, and it may also be faster. I wasn't sure from your from your performance results whether that was true, Roman, whether you were literally replacing if then else with a two-position case or not. But perhaps
yes, exactly.
if then else could be implemented more efficiently.
I mean, maybe it can be more efficient when both of your branches are pure, and it's a wash, really. It's not even worth complicating your compiler for that sake. Just use the case. Yep.
Can you hear me?
Yes.
So I was wondering about the limitation on negative numbers. Why is there such a limitation? Because it seems simple to just encode the numbers somehow and just, modify the semantics so that it makes sense.
So the case just literally performs a lookup in the vector. If you want to encode the integers, you can do that yourself.
Right, okay, I see. So you would need to modify case semantics, and yeah, that would be tricky. You'd basically need to add another case, type of case in the AST. Okay, thank you.
Yes, so it's not general pattern matching where you match something against the pattern that can be arbitrarily complex. This all is literally just looking up something in a vector for all versions of constants. So for Booleans, for integers, for lists, in future for data and for pairs and for unit, all of that is just a single lookup.
So I have a very simple question. If you give it a vector with 10 branches, right, you can case up to 10, right? It's
Yes.
okay. Well, from 0 to 9, I guess. If you give
Yes, yes,
10 options.
yes.
Okay, right.
Yes.
So it's variable length in that sense.
Yes. You cannot change the length of the vector at runtime in any way. You have to hard code it into your program. But otherwise, yes, it's variable length. So again, we just inherited that from sums of products. That's how sums of products work. And we just reused case for that purpose. Thanks. I am going to continue. That's an example of faster casing on integers. The issue with casing on integers is that unlike with if then else, we cannot just replace a single built-in. There is no single built-in for casing on integers. It's literally just like, as you've seen, it's equality checks chains. And it is not a single pattern in the compiler that we can replace. So we didn't get many good results from integer casing, despite the fact that it should be way more important than Boolean casing. But we got some. This is one. Like, this is pretty great. Yeah, again, for such a simple change. Legacy branching on the list. I hope I got it right, but I've only been on the team for 7 years, so who knows? This is how we do casing on a list right now. This is how people do it on the blockchain. That's quite horrible. So you need the choose list will pick the right branch depending on whether this is nil or cons. This again, both of these are going to get evaluated even though you only need one. That's because choose list is again just a function, and functions always evaluate their arguments. If the list is nil, we are going to choose the nil branch, and if it's cons, we are going to choose the cons branch, but then we also need to extract the head of the list and the tail of the list. So that's how many? 1, 2, 3, I think that's it, 3 built-in calls and like 3 forces. Oh my God. And 4 forces actually. That's a lot of overhead. Again, for such a simple thing as branching on a list. And that's the new version. So again, just a single AST node, just a vector with 2 values, nothing fancy. Note how we use cons as the first branch so that we can omit the nil branch if we don't care about it. And this is the operational semantics, again, entirely trivial. If it's nil, then we choose the nil branch. If it's cons, then we choose the cons branch and we apply the cons branch to the head and the tail of the list. This is the same thing as we had here. So like this whole part where we extract the head and the tail, here we do it like this. And we can omit the nil branch, just like with Booleans, we were able to omit the true branch if we only cared about the false one. But if we only care about the cons branch for lists, we can omit it as well. This is so that, for example, we can re-implement head list and tail list. If I recall correctly, they were like 18% faster or something this way by using case instead of using the built-in. Yeah, these are some results. This is again cherry-picked. It's quite a massive performance improvement, and the size not as much, but like look at the memory, more than 2x, and the CPU more than 2x. Pretty cool stuff. Any questions? Okay. Yes.
So you see, hi, Roman. This is Phil. You seem to decide that you would have a cons branch without a nil branch more often than a nil branch without a cons branch. Was that
Yes,
based
exactly.
on looking at the corpus of actual existing code, or was it just a guess, or?
It is just more often the case that you have that you care about the cons branch than the nil branch. For example, what Philip DeSaro told me is that they often know the exact shape of the list that they are processing. They just need to verify that the shape is indeed as expected. And the way you do that is that you just like you simply process the list as you expect the shape, as you expect it to have the certain shape. And how we do that here is that we use case 10 times in a row. Say if we expect a list of 10 elements, we just use case 10 times in a row, and we only ever care about the cons case. At the end, we can verify that the list is nil after the 10 cases by using, I don't know, a built-in, the null list built-in, or by using a two branches case. But basically, in a lot of cases, you know the exact shape of the data structure, and you just need to verify it. And the cons case is also recursive, meaning that for nil, it's always like one little opportunity. You can have 10 nils in a list, but you can have 10 conses in the list. And so again, the conses are going to be more common.
Often you want to fail on nil. So you expect to have an element there. If there is no element, you want to fail the entire contract. So
Yeah.
often that is the case, that you know, like you usually know what list you have. You build the transaction before executing the contract. So you know how many inputs, you know if you have a list and a redeemer, you build the redeemer, so you know what you're working off. If that is not the case, often you are just to, okay, I am being attacked, I will just fail the transaction.
Okay, thanks.
Let's continue.
Yeah, it's just second, Rema. So
Yep.
I noticed on the previous slide, there's a big difference in CPU and memory, but not much difference in the term size. Whereas with the previous case, we had quite a big difference in the term size as well.
I don't really know what's causing this, sorry. So what's likely is happening, okay, I think I can figure out what's happening. We usually bind case list as a function. So if you bind it as a function, you bind it once. That's now going to be a much more efficient function, but it's still just one function. So you make it smaller, but even though you make it a lot smaller, it's just a single function. It's not going to affect the size of the contract a lot, but it's now much faster.
I'm just thinking if what I thought. Hi, Roman. I was thinking that I think that I know the answer to Kevin's question, but now I'm not so sure I do. So this test in particular uses the as data way of compiling data types. So it compiles them to data. And when it compiles them to data, that means that data types themselves are basically big built-in lists, right, with pairs and so on. So maybe that, I was thinking that maybe if you had something which is based on SOPs, maybe the impact would be different. But now I realize that there might not be an actual connection in terms of, you know, program size. So yeah.
Yeah, I think it's probably my version where you have one single function that is a lot faster and is a lot smaller, but since it's just one function that is a lot smaller, the overall size is largely unaffected, but the overall performance is affected a lot.
Yeah, that sounds more reasonable.
Okay. And we made casing faster in general for data types whose constructors have a non-zero number of arguments. That works for both SOPs and things like lists and pairs. So 11%, 12, 13 in general for a very, very specific benchmarks. I think that's fine. Yes, and that's the implementation details that you were not looking for. This is what powers the whole casing on built-in machinery. It's this type class and its method. You take a constant. This is how we represent a constant. It's multiple, and this is a vector of branches. And you return either an error in the text form or this head spine thing. What this is saying is that the result is either just a term, so just a branch. For example, for Booleans, we return one of the branches without evaluating it. It's the CT machine that is going to evaluate it subsequently. Yeah, so we just return one of the branches directly, or return one of the branches applied to some constant. This is the head spine thing. Spine is just, view it as just a list. So this is for lists, for example. For the cons branch, we have to apply the branch to the head of the list and the tail of the list. And the head of the tail will become a spine. And this thing here will be a term, the cons branch itself. Any questions here? Yes.
It's not regarding specifically this because it's pretty similar to how const work, in the meaning that fields of the const are directly applied. I was more thinking about data. Does it work on data? And if so, how, like, for example, in the case of list, we apply the head and the tail. Those are operations that are done in order to extract the fields. Instead, in the case of const, the fields are already quote-unquote evaluated and we just apply them. So there is some extra operation in order to extract the thing to apply. How does that reflect in the costs?
So that's future work. We will come to data shortly. I don't have much to say about data, but I will say something.
Okay.
So just please be patient. Any other questions? Okay. And this is an implementation for Boolean, how we do casing on Boolean. It's an instance of the case built-in class for our universe of built-in types. We calculate the length of the branches, how many of them, and we verify that the given constant is a Boolean. This is how we do it, by matching on the type tag. This is the type tag of the constant. And then we case on the Boolean on the Haskell side. If it's false, then we are only fine if there is only one branch or two branches. So we don't allow 3 branches, we don't allow 0 branches, only 1 or 2. If that's fine, then we just look up the false branch. it's going to be the first one with the index 0. Similarly, for true, there has to be 2 branches, and we look up the second one with the index 1. Otherwise, it's an error. That's the whole thing. Questions?
I'm sorry, Romain, I'm going to be bothering you.
That's good.
So in case of Booleans, we cannot have a third branch, which I know is not useful in the execution context, but it might be useful sometimes for metadata. So in this case of Boolean, it just fails if there is a third, even if we know it will never be used, right?
Mm-hmm.
Okay.
Yes.
Cool.
I mean, we could allow 3 branches. I wouldn't really mind that. If people want that, then yeah. I guess we are going with the least with the minimal working implementation. So we do not need 3 branches for this to work, and so we just forbid them because we are paranoid that maybe someone will put 3 branches and expect certain things to happen, and they wouldn't happen. Okay. And these are all the changes that needed in the CDK machine. We amend the returning mode of the CDK machine. Oh my God. It only used to work on the conster, which is the value for the conster node of the sums of products thing. Now it also works on vcon, which is an evaluated constant. This is some pseudocode. It's a bit more complicated than that, but that's basically the idea. So we just case on that constant, and if it's a single branch without any arguments, we just continue evaluating it. So for example, if case false branch, true branch, that's going to be false branch, and we immediately start evaluating the false branch. If there is some arguments, so it's not just the branch, but branch with arguments, then we put the arguments into the frame and continue evaluating the branch. So same idea, is just that we also put aside some arguments to be evaluated later and fed to the evaluated version of app. Again, that's it, very simple stuff. Finally, branching on data. So the whole reason why we are doing this thing is that because we want branching on data. That's the most crucial part, and this is how it all came to life, just because I was thinking about branching on data for way too long. Again, I didn't really want to optimize any Booleans. That just happened as a byproduct of branching on data. I do not show you the old branching of data because it's just not going to fit on slide. So here's the newish branching on data. This is not the one that we aim for, but this is an improvement. We are going to extract from the conster data, from the conster constructor of data, it's what it carries, and that's going to be an index and a bunch of arguments. This case works because we also implemented case for tuple, not just lists and integers. So with case on the tuple, extracted from unconster data, then the case on the integer side. This is the part that was particularly slow with the current version of branching on data. Currently, you have to do the whole if I equals 0, if I equals 1, etc. dance. But with case on integers, we can just case directly, and you go into the right branch. Oh, I should have made it like this. Sorry, forgot. It's a vector. Yes, you go into the right branch and you apply that branch to the right arguments from the constructor. Apply to list isn't a thing, so you have to define it yourself. You can do it as we just discussed, where you kind of like just use case on the list 10 times and extract all the arguments. But in future, we want to improve that. We want to make this better. Also, we want to be able to case on the constructor of data here directly. So directly on this data, not on this like built-in without calling built-in, like forget about built-in, just casing on the data directly as it was an integer, because we would expect the const node there, we will case on the integer inside the const node directly. And this avoids one case, one built-in call. That's good. So the whole thing is going to become faster. We're just working out how to make it faster. But in the meantime, okay, I don't know how to clear all the mess that I created here. But in the meantime, this is the way to do casing on data. We haven't implemented it in the compiler yet, but it is available in UPLC. So if you want to beat us to it, if you're an Aiken person or Plutarch person, then you can do it. And proper new branch on data is to be done. Questions?
Okay, so I guess technically passing data as is fails. It only works on pairs and integers, right? I cannot
Yeah,
pass.
yes,
Okay.
yes. If you pass data as is, it will fail.
Okay, and then I'm not sure about still the costing that I asked before, but maybe I wasn't clear. So when we do add spine, in the case of const the old way, the arguments are passed as is. There are some implicit operations instead in the case of unconst. In case of pairs, implicitly they call first and second, and in case of lists, implicitly they call also add and tail. So how is that reflected in costing? Is that for free?
Pretty much. You do not call the built-ins. You don't call first head or second head directly.
Yeah.
All of that happens on the Haskell side, where it's much less expensive than calling the built-ins, and so it comes pretty much for free.
Cool.
Because you have all the overhead of SOPs, you have all the overhead of keys, of looking up the vectors. Just extracting a couple of elements from the pair, it's nothing.
Cool. Yeah, pretty cool. Thank you.
Yeah, that is how it works for Boolean integers, unit as well, by the way. Choose unit, so we have the choose unit built in. If any of you, for some reason, uses this built-in, move to case now, because it's 90% faster, but I have no idea what would anyone use the choose unit built-in, so maybe if you want to ensure that something is not an error, I don't know. Anyway, so we have all of that for pairs, lists, blah, blah, blah. But for data, it's more complicated, because what we want ideally is to perform multi-binding of arguments that the const node of data stores. And that is a linear amount of work. It is non-negligible. It's not extracting a couple of elements from a pair. It can be potentially very expensive. So we've been discussing it a lot, how we are supposed to do it. My personal idea is that we should create a separate AST node, call it let, and make that let bind multiple variables at the same time, and then make also that let work on constants and not just on regular terms. So that would be like a completely new AST node with like its own costing that differs from all other AST nodes, because all other AST nodes, they are constant cost, but this one is not going to be constant cost. So this is very far-reaching, and like it will take a lot of time to get there, because for occasional constants, we had everything available to us. It was very easy to just create the whole thing with what we already had. But adding a new node that is different to all other AST nodes, that's going to take time. And it will be hard to cost.
Hello, can you hear me?
Yes.
So I guess I just wanted to ask, I might have missed it, but when does this become available?
The next Plutus release, so Plutus V4, it's all already on master. It all already works. I'm not entirely sure if we have any end-to-end tests for it, by the way. Do we? I don't know. But other than that, it's in the code already.
Cool. Yeah, sounds good. Thank you.
Actually, I'm not even sure if it's Plutus. I'm not even sure if it's Plutus V4 because we probably don't even need a new Plutus version. This is entirely new functionality, which means we don't need to support any kind of backwards compatibility. So we can just, with the next hard fork, we can just release the whole thing. It's probably going to be the next hard fork and not the next Plutus release version. But you should ask that question to the end because I'm clueless.
I'll go with the question. Can I go? Or do you want?
Yeah, I was just going to follow on, and so I've been discussing, hard fork scope with Xiang and with Jess. So I think casing of constants is part of the proposed scope for Plutus version, for protocol version 11, providing it's ready, and that would then be early in 2026. And if you don't need a new Plutus version, that's great. Jess, I understand, is going to be here tomorrow, so we can have the discussion with her and confirm that.
Perfect. We are quite over time, so if you people want to go, I can let you go, or you can keep asking questions, and I'll keep answering them.
There is a case to use, pardon the pun, cases on unit, and that is terms that have side effects, namely traces and errors. Usually, like at least, if I remember correctly, how I do it, but I cannot speak it for compilers, assertions can be optimized to be if-then else's. So you assert and then either fail or continue. And traces can be optimized to take whatever next term is and then just trace whatever you want to trace. So
yeah, but you can get the same with just a function application.
Yeah. No, just saying, like, there is the case to use cases on unit, but I'm not sure. I'm not sure.
Sorry, that's why I wanted to add cases on unit, because precisely, hopefully it is faster than just function application. I was talking about the uselessness of choose unit, the built-in.
Yeah.
But yeah, for casing on units, I imagine that is how contracts are going to be written eventually. Instead of doing if then else error, people will just use case on unit and put the condition into the scrutiny.
Okay, and yeah, I think that was my question. That's it. I don't think anybody else has a question.
Right, Roman, there's no more question. Do you want to wrap up?
Yes, I don't have any conclusions. We should have done that earlier. That's my conclusion.
Okay, thank you so much, Roman. Give it up for Roman.
Thank you. And sorry again for not making it to the meetup.
Thank you so much, Roman. It was lovely having you remotely as well. Oh, hang on one second. Anna has got a question. Oh, she's got something to say.
So I am wondering if you thought about what changes we would need to make to the meta theory to include these changes to the UPLC language, basically.
I have not.
Okay.
I would imagine that they're not very hard. So do we even have a doing distinguish between different universes in the meta theory, I thought it was just like one hard-coded universe. And that means you don't even need to have any sort of type classes. You can just implement the logic directly. Even if it is customizable, it should be simple anyway, because again, if it was so simple for the implementation, I can imagine it will also be simple for the formalization, but I haven't thought about it.
Okay, thank you.
Okay, I think that's it for your session, Roman. Thank you very much. I think we can log you off. Thank you.